Okay, so here's another video about a family of triangles, these magenta actually polygons, known as harmonic polygons, which are actually inversive images of a family of regular polygons. So let's draw the inversion circle here. I'm going to place, is that what I'm doing? No, this is not what I'm doing. I'm actually taking this regular polygon here and I'm imagining a unit circle centered at this point here labeled as inv. And I'm going to construct the magenta polygon with vertices at the inversions of the regular vertices with respect to a circle centered at this point inv that I can select. Now, as I rotate my regular family within its own circumcircle, like so, okay, the magenta harmonic family rotates within its own circumcircle. The reason the magenta family is inscribed in a circle is because the inversive image of the circular motion of the regular vertices is another circle. Okay, now of course I can select this the location of this inversion point, and that's going to give me a slightly different family of harmonic polygons. And right now I'm choosing n equals 6. Now harmonic polygons are equipped with a very special point known as k, or the symmedian point. And for even n, the construction of k is simply let's see if this is what I want. Yeah, so it's simply the intersection of the major diagonals of my polygon. When n is odd, you actually have to use these quasi-diagonals, which are lines that connect each vertex to the opposite point of tangency of the family with its elliptic caustic. So this is actually a Poncelet family harmonic. There's a Poncelet porism here, and I'm not showing here, but this family is tangent or envelops a an elliptic caustic. All right, so very good. This family was studied in 1888 by Casey in his book called The Sequel to Euclid. I'm going to leave a link in the description. But and I've made a couple of videos about this family previously. But what's germane to this particular video is the following. We saw before that. Let's say here I'm going to light up an inversion circle, second inversion circle, whose center CM I can position anywhere in the plane, right? Okay. Now let's go ahead now and turn off the regular family. It's no longer important here, and I'm just going to focus on what's happening to the polygon whose vertices are inversions of the harmonic vertices with respect to the circle. So let's light it up. There it is. So it's this orange polygon, and let me actually make this orange polygon become a bit fleshier. And to do this, I'm gonna choose a harmonic family that looks like that. Actually, not so. Let's go to the other direction. Always representing the center of the circumcircle of the harmonic family. And here you can see this family of orange polygons, whose vertices are inversive images of the original harmonic. Now, Casey says in 1888 that the inversive image of an inversive family, of a harmonic family, is itself a harmonic family. So you can expect this orange family here, as I rotate everybody, to also be a harmonic family. Okay, and I can change my center of inversion, of course. I can place it anywhere. It doesn't have to be on the x-axis. It can go up to over here, and I have this family of inversive images of a harmonic family, which was also harmonic. Now, one thing we saw in the last video was that, let's go ahead and draw the symmedian point of this family. Okay, now one really interesting property was, first of all, the symmedian of this new family, because the family is harmonic, is also stationary, as is the center of its circumcircle, which is shown here by this orange dot, and here's its symmedian. But what we saw in the previous video was that if I actually executed a rigid rotation, so I'm going to freeze this family here, and I'm going to execute a rigid rotation of this polygon here, and let's draw the construction. So the midpoint of the major diagonals of my inversive image harmonic polygon. What we saw was that if I rotated this polygon here with respect to its symmedian point. And notice I'm actually rigidly rotating the entire frozen harmonic magenta polygon. I'm going to get an interesting motion or sort of dynamic to its inversive image with respect to this dash green circle. But what was really remarkable was that over this family, the symmedian point of the inversive family remained stationary. So let's actually focus on that a bit more so we can see it. And perhaps I can do this by exaggerating a little bit my inversive radius. So here's the symmedian of the inversive family. And when we rotated this guy with respect to its own k rigidly, that k inverse stayed mysteriously frozen. Speaking with a colleague, he told me that this could be a phenomenon taking place in hyperbolic space, and we're still analyzing what's going on here, namely that this is the center of this inversive harmonic in the Klein model of hyperbolic space, the Klein disk model of a hyperbolic space. Okay, now let me show you a new phenomenon here. What happens now? So let's now go back to the original situation, and let's see here. I'm going to place my inversion circle back over here. Let me reduce the size of my inversive image, and let's recenter that. Very good. Let's put this guy right at 0, y-axis, so I have a perfectly horizontal line connecting the center of my harmonics and my center of inversion. This is without loss of generality. Now I'm going to light up two other centers here, or two other points rather. I'm going to light up the limiting points of the circle pair, circumcircle of harmonics and Brocard circle of the harmonics. The Brocard circle of the harmonic family is a circle whose diameter is the segment KO, where K is a symmedian and O is a circumcircle. So here's a Brocard circle of my harmonic magenta family. Okay, it's that brown circle over there. Now you can actually now compute the two limiting points of the circle pair comprising the circumcircle and the Brocard circle. And let me actually make this family be a little more eccentric so we can see these two limiting points. And let's look at where they are. So the two limiting points, L1 and L2 of the pair circumcircle Brocard, are shown here. And here's their midpoint. Okay, now likewise, I can also show the limiting points of my inversive family. Let's go ahead and show them over here. And again, I have to make this thing maybe less eccentric so we can better see them, like so. And let me turn off my Brocard circle, which is no longer necessary. I'm going to scale this up a bit, and I'm going to move this to the left. And now let's go ahead and gyrate, not like that, not like that. Let's gyrate our family, like so perhaps. And I had the perfect situation before, but now I may have messed it up. Let me find a better location here for these limiting points. I want them to be very visible to you guys. There it is. I think now it's visible. So yes. Yeah, so if I scale this out a bit, you can see that the other limiting point is over here of the original family. Here the two limiting points, the zero circles in the pencil of the Brocard and the circumcircle. And we can also see the limiting points of the inversive family. Here they are L1 prime and L2 prime. Now as I gyrate my family, my harmonic family, the four limiting points are stationary. Both those of the original family, here they are. And by the way, this first limiting point here coincides with that inversion, the first inversion center that I did for the regular polygon. Okay, so that inversion center coincides with this limiting point. In fact, the limiting points of a harmonic, limiting points of the pencil defined by the circumcircle and their Brocard circle, these two limiting points, L1 and L2, they are inversion centers that will take a harmonic back to two families of regular polygons. Okay, but this is not germane. What's germane here is the following phenomenon. Let's move this guy to the right, to the left. Let's scale. Let's move this family or this whole scene to the left. So we're not looking at the outer limiting point here. I can scale this out so we can see it. Perhaps it's better to look at it this way so we can see everybody at the same time. Yeah, let's try it. Let's try it like that. So limiting point 1 of the harmonic, limiting point 2 of the harmonic, the midpoint of the limiting points, and here are the 2 limiting points of the inversives. Now, as I animate this family, everybody's stationary. Now, what I'm going to do now is I'm going to freeze the family, okay? And I'm going to not rotate about K as we did before, but I'm going to rotate this guy rigidly about this limiting point L1. So let's do that. I'm going to rotate this family, this magenta family, about, so rigidly rotated, pivoted about its first limiting point. Let's do that. And I want you to check out what's happening to the limiting points of the inversive family. The nice phenomenon here, and let's scale that up so we can see this really nice, is that as I rotate the magentas about their first limiting point, and let's do this dynamically, like so. So this is a rigid rotation of the magentas about this limiting point. The first limiting point of the inversive family is put. What if I rotate about the second limiting point of the magenta family, which is out to the left, okay? So it's a pretty big rotation. Let's actually scale this out so we can see what's going on. So there's a rigid rotation of my magenta family about the second distal limiting point. And let's look at what's happening to the second limiting point of my inversive image. So I need to do this. I need to take this to the left. And now you can see that the second limiting point, not the first, is stationary. Scale this up. Perhaps if I change my family just ever so slightly, this becomes clearer. Yeah, so there it is. So what's happening is that limiting point is staying put. You can see it put here. And this new configuration. Okay, so if I rotate about one limiting point, I cause one of the limiting points on the corresponding limiting point on the inversive to be put, and if I rotate the other limiting point, I cause the second limiting point to be put. Okay, so we have three phenomena. Rotate about K, the K of the inversive is put. Rotate about a first limiting point of the harmonics, a first limiting point of the inversive family is put right here. Rotate about the second limiting point of the inversive family is put. Alright guys, this is pretty much it. Thanks for watching. Pretty crazy stuff. And here's a complete scene of rotation of pinks about second limiting point, or rotation of the pinks about their first limiting point. Showing this point put. Alright. Thanks for watching. See you in the next video.